This is continuing our discussion from last time, and this is one of the central techniques for modern control theory in terms of stability. And this is what I want to talk about today. Over the last 2 lectures, we talked about stability, but from the concept of eigenvalues of the A matrix, or poles, roots of the polynomial denominator for the transfer function. Now, this is introducing a new concept from the energy viewpoint. Instead of just trying to solve, like figuring out where the poles or the eigenvalues are, this one is built entirely on the concept of a single function. You don't need to consider all the eigenvalues, but you look at one single function, it's like an energy concept of the entire system. Can you guys see? Good? All right. So this is looking at one single function, and then from this single function, you can tell how the system is going to look like time-wise. So if you see the energy is going down eventually to 0, then you can conclude that we have stability. So we'll be introducing some concept about this person, Lyapunov. We talked about the name last time. So we'll be talking about the Lyapunov function and how it connects to energy, to describe energy for overall system. And this relates to linear algebra. So we'll be talking about symmetric matrices, how it relates to energy function, and then going beyond, moving a little bit more towards the energy side, from symmetric matrices to positive, definite, or PD matrices, and then to PD functions. Then we'll conclude with the Lyapunov series and Lyapunov equation. So that's my goal. All right. There will be some relevant mathematical tools today, and then we'll be talking about the theorem, both stability theorem and instability theorem. We'll talk about continuous time case as well as discrete time case. Now, a more formal statement of the concept that I just described. This is no need to explicitly solve the system response, no need to solve the eigenvalue, no need to solve e to the power of at, but just looking at the system from an energy perspective. And it fits. One very important result here is that this energy perspective, it works for both linear systems, x dot equals ax plus bu, that we talked about last time, but also nonlinear systems and even time varying systems. So this is the most generic tool for stability of dynamic systems. All right. Let's start from the easy case, the energy perspective. In context of a spring mass damper, where you have the velocity information, the derivative of the position is velocity, and the derivative of the acceleration is your total force from the spring, from the k coefficient, and the damping coefficient, damping term, divided by the mass. So you see that essentially ma equals total force from Newton's law. So you can imagine that this kind of system is going to be stable, right? If you have like a mass moving on a surface with a spring attached to it, and then the surface has friction, eventually it's going to stop. The energy is going to die out, go to 0 eventually. So you can check the eigenvalues of this system, the A matrix for this system, they are all stable. So this is what you can check mathematically. But if you look at the system from the energy perspective, you can see that the total energy, this is just a spring and mass, right? So there's spring is containing some energy. So it's potential energy in the spring, half of k times the position square, and the kinetic energy stored in the mass, depending on the velocity. So half of m times the velocity square is the kinetic energy. Now, if you take the derivative of this energy function, of this total energy, you can get, taking derivative, looking at here, these are scalars, and position is a function of time. So when you take derivative of e with respect to time, This is how energy dissipates with respect to time. Then is derivative of this one is half of k times 2x1 and then x1 derivative. And then it's k x1 times x1 dot. So similarly for the second term, it's m times velocity and acceleration. That's from just calculus. Now, this is straight out from the functional analysis. Plug in now the position and the velocity, they have relationships. They are governed by these two ordinary differential equations. These are the models of the system. So plug them in, more specifically plug in x1 dot to here and x2 dot to here. Then you can get the, let me write it here. So you will get k1 times x1 times x1 dot, which is x2, plus m times, this is k times x1, there's no k1. And then plus m times x2, x2 dot. So it's negative k over m x1 minus b over m x2. And then you can see m cancels out. And then you have k x1 x2 plus minus k x1 x2. So this term is also going to cancel out. And the only thing that remains is negative b times x2 squared. So you can see this is the derivative of the energy. And because the damping coefficient is positive, and this is x2 squared. So this is always positive or 0. So this whole term is going to be less than or equal to 0. So that means if you have an energy function that's positive, and then the derivative of the function is negative or 0, then that means the energy is going to reduce, right? The energy is not going to increase because its derivative is negative or 0. So this is the concept of the energy dissipates or is dissipative. So that's a good thing. At least we don't see like the system is going to go crazy, right? These two terms, position velocity, is not going to go unbounded because the energy is reducing. Now furthermore, there's another observation. If you think about the case when this derivative is going to be 0, then you will see that the derivative, the energy is only is not going to stop until x1 and x2 are 0. So in other words, we're trying to argue that the two state, x1 and x2, is going to go to 0, meaning that it's asymptotically stable, right? So you can let's take a look at the math. So take a look at when the derivative is going to be 0. So it's only going to be 0 when x2 is 0. Now take a look at the equation. x1, x2, the only equilibrium point for the system is that, so equilibrium point is the concept that x1 dot is 0, x2 dot is 0. So the only way for these two equations to be 0 is x2 being 0, and if x2 is 0, x1 must be also 0 in order to make x2 dot to be 0. So that means the only equilibrium point for the system is the state being at origin. Even if, like, when, suppose at some point your position, your velocity is 0 and your position is not 0, then that means your motion is not going to stop, right? So if your velocity is 0 and your position is not 0, then the velocity is going to continue change. There will be acceleration. So the system is not going to stop at any point other than this point. So therefore, when we see that the energy dissipates and it stops, the energy stops dissipating at the derivative equal to 0 point, then that means the energy is going to keep decreasing towards both x1 and x2 being 0. It's not going to stop when only x2 is 0 and x1 is not 0. All right, so it's again, if you think about the physics, a moving mass, then if you have like, let's see, the physics is like the velocity is 0 and the position is not 0. So it's like you have a spring and then a damper. It moves left and right. Then maybe at the furthest point, let's say here, then it's going to make a turn. And at this point, the velocity is 0, but the position is not 0. It's not at the equilibrium point. So it's going to keep coming back. It's not going to stop here. So the energy is going to continue to dissipate from this point on until it goes back and forth and stops at this origin, at this equilibrium point. So that's the concept of how physically the energy dissipates to 0. So what we did is a spring mass damper system, and things can be more complex and it will work. So while system can be a general continuous time or discrete time system, and we don't have an A matrix to compute the eigenvalues at all. We have a general function f. It can be time varying, it can be nonlinear, it can contain x squared, x to the power of 3, etc. And this concept of the energy always holds. Our assumptions are for these kind of systems, you can see that we don't have an input, so we are considering just the system response released under some initial conditions. Let's assume, for simplicity, without loss of generality, assume that the origin is what we are looking at, is the equilibrium state. And this time it's no longer just a spring mass and we can compute the energy easily. This time it's a general system and the state can have different meanings. So the energy function will become the concept. The concept of the general energy function is going to generalize to a Lyapunov function. So it's a description similar to a general function. It is describing, it's a scalar function, right? You have state, maybe have multiple elements in the state vector. But you only consider just a scalar function of the state. So in the continuous time, it's x and t. In the discrete time, it's x and k. K is the time index. We will be talking about properties of the state through looking at this energy-like Lyapunov function. And we'll be using the tools matrix formulation, linear algebra, and symmetric positive definite functions. All right. Some tools, some relevant tools first. Matrix is really powerful for describing energy-like functions. So if you think about what we did, we have this one, the energy function for spring mass damper. We can write it this way, but it's nothing but we can write it also this way. So we can stack the state vector like this and then put the transpose of the state vector in the beginning. So this is essentially, you're computing, this is a row vector, x1, x2, multiplying a matrix and then multiplying a column vector. So you can check the elements computations are x1 times is essentially, so talking about the first two, is k times x1 is the first column times x1, first row times x1 plus the second row times x2. So it's k times x1 plus 0 and then 0 plus m times x2. And then multiply things out, you're going to get half of k x1 squared plus half of m x2 squared. So this energy-like function in our spring mass damper is essentially a vector matrix vector multiplication. Things can get more interesting. So if you have, let's say here, not just these two elements that contains squares of the states, but you have a cross product, x1 times x2, is also exact the same format structure. A vector times a matrix times a vector. So you can check x1, let me do it one more time. So this one, this row vector multiplying this matrix is going to give you the first row times x1 plus the second row times x2. And then this multiplying the column vector. Then you get half of k times x1 squared plus half of x2 times x1, and then plus another half of x1 times x2, so giving you x1 times x2 here. Then plus half of m times x2 squared. The main observation is that the diagonal elements is going to contribute to your square terms, and the cross off diagonal elements is going to give you the cross product terms. And then you have both cross product elements entries is going to contribute to the cross product term, and you need half from each entry here. That's why it's 1 and it's half 0.5 here. Okay? Things can get even more interesting if you have not just a square term but also cross product term and then constant term. Is again a vector transpose times a matrix times a vector. You can check, double check. It's like you look at things in a little bit block matrix perspective. The first block, you can see this is exactly this part over here. So this times this give you the first portions, the three terms. And then the last one is like 1 times c times 1, and then give you c. So functions can be written in a matrix vector form. That's the key observation. Now once you write it this way, once you figure out this matrix P that's going to describe your function, then you can get all kinds of properties out of the function by taking a look at the P matrix. All right? Out of the box, this is immediate observation. We can see that the P matrix from these examples here, P matrix is symmetric. Right? So all these matrices are symmetric. So general quadratic functions can be put in matrix form where you have a P matrix that's symmetric. So that's the first core component of analyzing the Lyapunov function. So symmetric matrix is very important. It connects very quickly to energy-like functions. Now, symmetric functions, in a more general sense, this is a fantastic function. It turns out any function, you give me any matrix, it can be expressed as some symmetric function adding to another skew symmetric function. What I mean, let's see, by this example. Okay, so symmetric functions, symmetric matrices are A equals A transpose. As a recap, skew symmetric functions, skew symmetric matrices are A that satisfies A equal to negative of A transpose. So this is a symmetric function. This is not symmetric, but is skew symmetric. And then this one is not symmetric and not skew symmetric, but it can be decomposed as a symmetric matrix and adding to another skew symmetric matrix. All right? So you can see that a quick example, a general matrix decomposed into a symmetric matrix plus a skew symmetric matrix. But things can get, like, sometimes non-trivial matrix can also be decomposed into this structure. So let's take a look at 1, 2, 3, 4. This is most simple example. It doesn't look like symmetric at all. It doesn't look skew symmetric at all. But you can see that it can be decomposed as this. It's 1 for the diagonal elements, and then in the off-diagonal elements you get 2.5, 2.5, and then here you get negative 0.5 and then plus 0.5. Then adding up together you get 1, 2, 3, 4. So more generally you can check, give me any P matrix. You can do the decomposition as following. You can do P plus P transpose divided by half, and then P minus P transpose divided by half. Right? This one, obviously, if you do the transpose, then it's exactly itself. And then for this one, if you do the transpose, is P transpose minus P divided by 2, which is negative of itself. So symmetric matrices are really powerful matrices. All right. So another concept built on top of a symmetric matrix. It's about the concept of you have multiple columns in a matrix. And if these columns, for example, like this, 1, 1, 0, 0, or 1, 1, 1, negative 1. If these columns are linearly independent, so this one is obvious, the first column independent from the second column, and this one is also linearly independent. The second column is no way to be expressed as the first column. And then these two columns are also orthogonal to each other, perpendicular to each other, right? So perpendicular means if you multiply these columns out, the dot product of these columns is going to give you 0. So if you are used the notation here, A1 is the first column and A2 is the second column, then A1 transpose times A2 is 0 for both of these matrices. So that means A1 is orthogonal to A2, and if this happens to every columns of the A matrix, then A is called orthogonal. And it can be more compactly verified by doing this A transpose times A or A times A transpose. If it equals identity, then it's called a orthogonal matrix. Right? You can check for this matrix is very easy. If this matrix is A, then A transpose is also identity. So A transpose times A is identity times identity, and it equals identity. For this matrix is similar. If A is 1, 1, 1, negative 1, then A transpose is 1, 1, 1, negative 1. So A times A transpose is going to give you, you can check, is going to give you the first element is going to be 1, 1 times 1, 1, so it's 2. And then the second element here is going to be first row, second column is 0. Similarly, for the 2, 1 element is 0. And then for the 2, 2 element is 1 times 1 plus negative 1 squared, so it's also 2. All right. So this one gives you 2, 2. Let me do a little bit of edit. Let's do square root of 2 for all the entries. Then this time it's going to give me 1 over square root of 2 square, and then gives us identity. All right, that's another example of a orthogonal matrix. If you multiply itself with its transpose, gives you identity. Then all the columns of the matrices are orthogonal to each other. And then when you multiply out, they have unit norm in the vectors, right? So this is a little bit more detail here. This one being 1 means that when the first column times the first column, the norm of the first column, this happens, let me do it this way, A transpose A, this is easier. So let's do A1, A2 transpose, A1, A2. So I want to show you guys that this identity, this one element here, means that the columns, the lengths of these columns are normalized to 1. So that's my goal. Take a look here. This is A1 transpose, A2 transpose times A1, A2. And it equals first row, A1 transpose A1, A1 transpose A2. Second row, A2 transpose A1, and then A2 transpose A2. All right? This is what I mean. If their product gives you identity, then that means, first of all, they are orthogonal to each other. 0 is here, so that means they are orthogonal. And second, the length of these individual vectors, A1 transpose times A1 and A2 transpose times A2, is normalized to 1. All right? So that's the meaning of an orthogonal matrix. So the columns of A, they form a basis. They are all linearly independent. They are orthogonal to each other. And then they are also normalized to unit norm. So that's a orthogonal matrix. The orthogonal matrix is going to come immediately helpful when we talk about eigenvalues and eigenvectors of a matrix. So when we talked about similarity transform, diagonalization, we talked about the concept of a matrix can be decomposed into A equal to T lambda T transpose, T inverse, right? This is the diagonalization result. Now, what we're going to show over the next few slides is this. If A is symmetric, then this decomposition is going to be tremendously simplified. So when doing the default form, you have to do a lot of things. You have to compute T out of all the eigenvectors and then do another inverse of this matrix. What we're going to show that when A is symmetric, this is very easy. So first, let's take a look at this one. Let's take a look at the lambda matrix if A is symmetric. It is a fact that if a matrix A, square matrix A, is symmetric, then this lambda matrix, it's impossible for a complex eigenvalue to appear. So symmetric matrix is always guaranteed it's going to give you a real eigenvalue. All right? So let's start with some examples first, and then I'm going to show you the theorem. Let's take a look at this matrix. 0, 2, 2, 0. The eigenvalues, you can do eigenvalue computation. Determinant of A minus lambda I is going to give you a determinant of negative lambda, 2, 2, which is lambda square minus 2 square. So all the eigenvalues are lambda 1 is 2 and lambda 2 is negative 2. So they are real. All right? Since it's different if it's not symmetric. Let's say if it's 2, negative 2, we talked about actually something similar to this one previously. The eigenvalue of this one, anyone remember how it's going to look like? 2i, right? Plus minus 2i. So you can do the computation, and this is the result. So it's not symmetric, it's skew symmetric, and then it gives you complex eigenvalues. And then this is all real. All right? By observation, you can already tell a matrix properties out of like how they look like. So let's take a look how this can be a little bit systematically shown. We're going to take a look at how, let's pick any eigenvector pair. Lambda is an eigenvalue, and the associated eigenvector is u. So let's take a look at, to show that lambda is real, what we're going to show is something like this. So A is a matrix and U is a vector. It's not directly obvious how we can show real or complex of these individuals. However, if we do this, if we consider multiplying U with its transpose, complex conjugate transpose, then this is a real number. So let's say if U is 2j, then U bar is 2 negative j by my notation, the complex conjugate of U, and then U transpose of complex conjugate times U is going to give you a real number. All right? Then in that case, if I want to figure out whether lambda is real or complex or not, I just need to take a look at whether this is complex or a real number. All right. Indeed, this is a real number, as can be shown in a few steps shown here. To show whether a number is real or not, we can do this. We can take a look at its complex conjugate. If the complex conjugate is not the same as the number, if it's j, then complex conjugate is negative j, then it's not a real number. If the complex conjugate in the end equals to itself, then it's a real number. All right, so that's our goal. In between, we can use basically this property over here. It's symmetric. First of all, complex conjugate of the whole thing multiplying together is nothing but taking the complex conjugate of the individual elements and then multiplying together. So it's going to be U bar becomes U, A becomes A bar, U becomes U bar. Now, because A is a real symmetric matrix, right? A is real, so A bar is A itself. So we got the second equality figured out. Now, because A is symmetric, so A equals A transpose. Now, because A equals A transpose, and then I have a U transpose, A transpose here, then this is AU transpose times U bar, right? So the first two transposes can be combined together. Now, once you recognize that, AU is nothing but lambda times U. So it's going to become lambda times U times transpose and then U bar. So the result then is clear from here. U bar and U, they are complex conjugate of each other, and if you do U transpose times U bar, it's going to be a real number. So this is a real number, all right? And it's this one over here, you can see that this equals now exactly this one. So both of them is going to equal to lambda u bar transpose times u. So this is indeed a real number. All right? So this is indeed a real number. Real number here, then if you divide them up, it is also a real number. There's no complex number is going to appear. All right? This is one of the proofs that I will do a little bit more carefully in class. And a lot of these proofs are just showing using these properties at certain steps. And then you will be able to figure out some of the equalities like this. But the key point, the takeaway message is the important thing here. If A is symmetric, lambda is also going to be guaranteed to be a real matrix. All right? We talked about another example, skew symmetric matrices. We talked about the eigenvalues are all imaginary, right? This is another theorem. Eigenvalues of skew symmetric matrices, all imaginary or zero. If you make a comparison, if you have matrix structure on the left-hand side and on the right-hand side you look at complex planes, then symmetric matrix is like the real line in a complex plane. The eigenvalues are guaranteed to be real. And the skew symmetric matrices are analogous to the imaginary line. The eigenvalues are all staying along the imaginary axis. And the orthogonal matrix that we talked about earlier is another special matrix structure. So it turns out if you compute the eigenvalue of orthogonal matrix, it's like the unit circle. All the eigenvalues are guaranteed to be 1. Yes?
So when we're saying orthogonal, we're saying we're actually orthonormal?
What I mean is precisely this one. It's identity. So that means the vectors are normalized to unit norm. Yeah. In the scalar case, it's like A times A, it's like A square, A times A bar. So this kind of matrix case, in the scalar case, is like computing the magnitude of a scalar in the complex plane case. So this equals to I is analogous to the vector have unit length. All right? Okay. Yes?
If the eigenvalues are magnitude of 1, does that mean that for the orthogonal matrix, does that mean they could be both complex with magnitude of 1 and real?
Yeah. So it can be it can be square, it can be this plus this, something like that. Once you see that, then you can quickly see from the matrix structure how the eigenvalue is going to look like. So we talked about this one already. A skew symmetric matrix, all the eigenvalues are on imaginary axis. And for this one, right, we can see it's symmetric. So the eigenvalue is going to be guaranteed to be real. And you can check, you can actually compute using the spectral mapping theorem, right? You can decompose this matrix into the summation of an identity matrix plus this matrix, a symmetric matrix. Then from the spectral mapping theorem, the eigenvalue of this one is nothing but 1 plus the eigenvalue of this matrix. And we talked about the eigenvalue of this symmetric matrix is plus or minus 2. So the eigenvalue of this one is either 3 or -1. Similarly, for this matrix, it's not symmetric, it's not skew symmetric. There's no guarantee that the eigenvalues are all going to be real or imaginary. Then you can check the eigenvalues, again, by spectral mapping theorem, is 1 plus the eigenvalue of 0, 2, -2, 0 is 1 plus minus 2j. So it's not exactly on the real axis, it's not exactly on the imaginary axis. Any questions?
Yeah. So does this works for any square matrix?
Yeah. Any square matrix, not just the 2 by 2. Okay? So another thing that we can show is this matrix is not orthogonal. If I do, let's check something quick. I want to create an example of this case. Orthogonal matrix has a magnitude of 1. Let's see if I can succeed from modifying something here. So these two columns, as you can see, they are orthogonal to each other, they are perpendicular to each other, right? And then they are not unit norm. They don't have unit length. So let's do square root of 5 times this matrix, or in other words, 1 over square root of 5, -2 over square root of 5. So this matrix, the columns, they are perpendicular to each other. If you do this times this plus this times this, going to give you 0. So they are perpendicular to each other. Their lengths of the column vectors are 1. Right? So if you do this square plus this square, it's going to give you 1 plus 4 divided by 5. So this is indeed a orthogonal matrix. So what are the eigenvalues of this matrix? It's nothing but the original matrix scaled by 1 over square root of 5. So the eigenvalues of this matrix is 1 over square root of 5, 1 plus or minus 2j. And then you can see the magnitude of these eigenvalues are precisely 1. So we indeed verified our third theorem. So orthogonal matrix, magnitude 1 eigenvalue. All right, so let's go back to the big picture. Why do we do that? It's because this original diagonalization can be complex to compute. Computing an inverse is something that you don't want to do for higher dimensional matrices in an exam. However, if it's symmetric, then it becomes this. So if it's symmetric, it turns out you can use U transpose to replace U inverse. And the intuition is that we talked about orthogonal matrix. What is so good about orthogonal matrix is, if you take a look at this, orthogonal matrix has this fantastic property that its transpose is its inverse out of the definition right here. Okay? So if it's symmetric, then it turns out these eigenvectors that construct this U matrix, okay, they are perpendicular to each other, and we can normalize it so that its transpose, its inverse is its transpose. So what this means, if you take a look at it more carefully, let's say the eigenvectors are u1 to un, and then the diagonal elements are lambda to lambda n, and then u1 to un transpose. So what this means is this. You can write it out and get so write this out is u1, let's do the first part, is u1 lambda 1, and then lambda 2 u2, and then at the end is the nth row of this matrix times un. So this vector, this row vector times this matrix is going to give you a row vector, and then this is a u1 transpose all the way down to un transpose. Multiply things out is lambda 1 u1 transpose plus lambda 2 u2 transpose, and then etc. So take a look at this, what this means. We may have a gigantic matrix A. However, as long as it's symmetric, we can decompose this matrix A into these very much simplified structures, right? It's the summation of these small submatrices. And these small submatrices, these are rank 1 matrix, guaranteed. So we have decomposed maybe a rank n matrix into a bunch of rank 1 small submatrices.
Doesn't that just turn into the sum of your eigenvalues? Because the U1 transpose equals the U1 inverse and say U2 of U1.
All right, so that's talking about here, right? So be very careful. That's another thing about these matrices. U1 is a column vector. A column vector times a row vector, this is a matrix. And it's not guaranteed to be 1.
Gotcha.
Yeah. Okay, so take a look at this. Let's take a break. Take a look at this more carefully and finish up all this statement. So this decomposition of a symmetric matrix into these sub-matrices is called symmetric eigenvalue decomposition, or spectrum theorem for symmetric matrices. And as we talked about, lambdas are the eigenvalues of A, and the U I are the eigenvectors associated to the eigenvalues, normalized to have unit norms, and U consists of these eigenvectors, normalized eigenvectors, and satisfy this orthogonal property. Its inverse is transpose. All right? So this intrinsically implies, so to prove this, there are few pieces to talk about. So the first piece is the eigenvalues are real, which we already proved. The second piece is that these, so for U to be orthogonal, we needed to prove that Ui times Uj, they are orthogonal to each other. So we need to prove that the eigenvectors are linearly independent and orthogonal to each other. That can be proved also not difficultly. It is a fact. If A is a real matrix, symmetric matrix, and then the eigenvalues associated with different eigenvectors associated with different eigenvalues, they are going to be orthogonal, guaranteed. So the proof is doing another trick is similar to what we discussed. Starting from this eigenvalue-eigenvector pair, which are vector equations, to go to a scalar value in the end, right? So the key concept of the proof is that from here, do consider Ui transpose times A Uj, and then eventually figure out that this term, it equals two things. It equals lambda I ui transpose uj, and it also equals lambda j ui transpose times uj. And because the same thing equals to two expressions, and we talked about the eigenvalues, let's say they are distinct, so they are not the same, right? So associated with different eigenvalues, then it must be that this is 0. I'll quickly go through the proof with you guys, and you can take a look at every details a little bit more carefully after class. So we're talking about looking at this. Let's take a look at the second part first. A times uj is lambda j times uj. So this scalar, it equals lambda j times ui transpose uj at the first place. Now, because A is A transpose, right? So it equals A transpose. Then you can see that this part can also create a eigenvalue-eigenvector pair. So more specifically, replace A with A transpose because of symmetric property. And then the first two components is AUI times T transpose, AUI transpose. So it's actually lambda I times UI transpose times UJ. So in that way, we see that we create these two different representations of the same number. So they must be UI transpose times UJ is 0. They are orthogonal to each other. So that's the proof, the main steps. So therefore, the symmetric eigenvalue decomposition can be very quickly constructed. If A has all these distinct eigenvalues, then you put up all these eigenvectors are orthogonal to each other, then normalize it so that all the eigenvectors have unit norm. Then you get a orthogonal matrix. On the other hand, if A doesn't have enough distinct eigenvalues, then it turns out things is not going to go crazy. Turns out we can choose multiple orthogonal vectors from the eigenvalues, meaning that if you have, let's say, two eigenvalues, but your matrix is 3 by 3, it turns out for one of the eigenvalues, you can always find two eigenvectors that are orthogonal to each other. That's a very important result in this proof. And the details to show that this can be guaranteed is provided in the textbook. Okay, so it involves a little bit more steps that we don't have enough space to go through in class. But it's the result is clear. You can have always orthogonal eigenvectors for symmetric matrices. All right, so let me ask you one question from this slide. We already know that the next time we see a symmetric matrix, you will know that eigenvalues for sure is positive, or it's real. All right? So let me ask you, if the eigenvalues are real, and I have a matrix A, can we guarantee that the eigenvectors associated to these eigenvalues are also real? Is this statement. If A is real and symmetric, and then eigenvalue is also real, and I want to compute eigenvector, is this real, or it can be complex? Real? All right. What do you think? What is the reason? This is real. This is also real. So this is a real matrix. So if I have a real matrix, we are solving this equation, right? A real matrix times a vector equal to 0, right? So what is the what is the tool that you use to solve a matrix equation like this in your undergraduate linear algebra class? Not linear algebra, might be the first class about solving equations of systems of linear equations. Gaussian elimination, right? So you do row operations, or you can do column operations. And you do that until like you see a lot of zeros at the left bottom, right? So if the matrix is real, you do these row operations, there's no way you can create a complex number in the rows, in the Gaussian elimination. Think about that, then you can see that you're going to get a real eigenvector. All right? Great. This one is cleared out. The eigenvectors, they are real, they are great. They'll construct a orthogonal matrix like this. All right? All the individual columns of the orthogonal matrix, because they are linearly independent, they are orthogonal to each other. So they actually consist of a basis, right? So they can form a basis. All the vectors in this basis, the n vectors, they are linearly independent. In other words, because this is a basis, you can actually express any vector, n by 1 vector, based on these eigenvectors, right? Because they are a basis. So this is super cool as well. Now, the last thing is more related to computation. If you utilize this fact, this little fact here, very smartly, you can solve a lot of problems very quickly. So the basic concept is this. Let's say you have a matrix A that's 2 by 2. And you solve, it's symmetric. And you can get eigenvalues, right? They are real. And you can get different eigenvalues, right? Let's say. So 2 different eigenvalues, and you can compute 1 eigenvector from the first eigenvalue. Now, because the fact over here, because the eigenvectors, they are orthogonal to each other. So once you get u1 out of lambda 1, then when you compute u2, normally when you compute the eigenvector, you have to do a minus lambda 2I u2 equal to 0 to get the second eigenvector. You don't have to do this if A is symmetric. So that's the key. And I will show that with one example. You can compute u2 very quickly after you get u1. And the example is here. It is 5, 7, square root of 3, square root of 3, so it's symmetric. And its eigenvalues, the normal computation, are 4 and 8. Okay, so not too tedious. You can get the first eigenvector. So a minus lambda 1I times t1 equal to 0. That means 5 minus 4, that's 1. 7 minus 4, that's 3. And then square root of 3, square root of 3 times t1 should be 0. So you can pick, for example, this one, right? You can pick negative square root of 3 divided by 2, and then half. So first row times this column is going to give you 0. 1 times this plus this times this can give you 0. Same thing for the second row here. So you get a 1 eigenvector. And then you don't need to do anything further. Because T2 is a symmetric matrix. So the second eigenvector is going to be orthogonal to the first eigenvector. So pick one that's orthogonal to this one, then it's guaranteed to be an eigenvector. I can pick, for example, this one. This is orthogonal to this one. I just swap the 2 rows and then change the negative sign to positive sign. So these are 2 orthogonal vectors. And then it's guaranteed this is one eigenvector. So let's take a quick look and verify that this is indeed true. Let's verify. Let me do it. Here. A minus lambda 2I, it equals, lambda 2 is here, so it's 5 minus 8, negative 3, 7 minus 8, negative 1, square root of 3, square root of 3. Let's verify that A minus lambda 2I times T2 is 0. So looking at, let's do multiplications. T2 is half of the first column, right? Plus square root of 3 divided by 2 times the second column. So this should equal to half of the first column, so negative 3 over 2, square root of 3 over 2, plus the second column scaled by square root of 3 over 2 times square root of 3, then negative square root of 3 over 2. So you got a negative here, negative 3, plus 3 here from this multiplication. And then you get negative sign here, positive sign here, so it's indeed 0. So that's a quick verification that this choice is accurate. Any questions? So far, we spent time talking about symmetric matrix. We understand that eigenvalues are real, and then the eigenvectors, they are orthogonal to each other, and the similarity transform, the diagonalization, is going to be super easy in this case. Now, the next class of matrices goes one more step beyond. So it's not just having these good properties, but it also has another very good property related to the energy function. This is called positive definite matrices. To start, let's take a look at the eigenvalues. So because they are real, right, we can order the eigenvalues. So we can do, let's say lambda 1, lambda 2, lambda 3 is 2, 3, 4, or something like that. We can order them. We can choose the smallest eigenvalue and then the largest eigenvalue. And then we can put them, we can have an order of these. If they are complex, you cannot do that. Complex numbers doesn't have larger than or equal to in this sense. So because the eigenvalues can be ordered, so we can talk about the smallest eigenvalue and the largest eigenvalue. So if all these eigenvalues, they are positive, then this is called the positive definite matrix. All right. So let's take a look at this theorem more carefully. All right. Why do we do this? We talked about energy functions to start with, right? Energy functions are quadratic functions that look like this. It's a vector transpose times a matrix times a vector. All right. So this connects very intimately to energy functions. So we want to figure out, right? Energy function, we want them to be positive. The energy, we want it to be positive. So talking about these guys, we want to be able to understand whether this type of construction, this type of energy function, is guaranteed to be positive or not. Okay? So this theorem connects the positive notion of the energy functions with the eigenvalues of the A matrix. So more specifically, this is what the fact is. If A is a symmetric matrix, right, we talked about we can order them. We can pick the smallest eigenvalue and the largest eigenvalue. So it turns out that the smallest eigenvalue and largest eigenvalue have a very specific format. So it's going to be the minimum or the maximum of an energy-like function, a quadratic function, divided by the length, the norm of the x vector over here. All right? The norm square, to be more exact. All right? So that's the two formulas. And I would like to show you that how these can be decomposed into small pieces that we talked about. So there are two important aspects over here. First of all is if A is symmetric, then we talked about the eigenvalue decomposition is going to be super simple. That's the first result. And Ui and Uj, they are going to be orthogonal to each other. You pick any two eigenvectors from here, they are going to be orthogonal to each other. So that's the first result. And then the second result is we talked about these eigenvectors, they form a basis, right? So these are linearly independent eigenvectors. That can express, you give me any x, right? You give me any x, I can find a decomposition into these eigenvectors. Let's say alpha I ui, straight out of the symmetric property of the A matrix. So then in this case, because of these two results, then we can see that X transpose, this energy-like quadratic function, it equals, just to put them in, times the spectrum decomposition, and then times X decomposed. All right? So it looks very cumbersome, a lot of terms. But if you take a look at these, the result is actually amazingly simple. So let's see. Let's look at these two parts first. If you look at it, it's lambda 1 u1 u1 transpose plus lambda 2 u2 u2 transpose, etc. times alpha 1 u1 alpha 2 u2, etc. So when you multiply things out, you're going to encounter this first term multiplying this is going to get lambda 1 alpha 1 u1 u1 transpose times u1. Then the second would be this term multiplying this one here. And what would that be immediately? 0, right? Because you get u1 transpose times u2. They are orthogonal to each other. So no matter how, for all these terms that comes next, because these vectors, they are orthogonal to this one, it's going to be all 0. So similarly for the second term in the first bracket, when you multiply this with that, u2 is orthogonal to u1, so the first term is going to be 0. It only matters when this multiplying the corresponding, the same term in the second bracket. It only happens, it's non-zero only if this second term here multiply this, the third term multiplying the third term over here. So it's going to be exactly something like that. All right, so that's the first observation. Now the second observation is this. Because U1 is normalized, it has unit norm, right? So U1 times U1 transpose times U1 is what? It's 1, and then this is also 1, and then all the things are 1. So this is nothing but lambda 1 alpha 1 U1 plus lambda 2 alpha 2 U2, etc. So it's almost as if when you multiply things out, you're just multiplying, you just put a scalar in this decomposition of x, alpha I, into multiplying this eigenvalue, right? So it's like eigenvalue scales this and then keep the same direction. All right, so putting the eigenvalues inside here, it looks almost as if like that. So that's the first piece. Now we can take a look at the remaining one. It's very similar structure. This one now is alpha 1 U1 plus alpha 2 U2, etc. times alpha 1 lambda 1 alpha 2 lambda 2, etc. Exactly the same logic. What will be the result? It's only going to matter when this multiplying with index 1 multiplying this term with index 1 here. So the result is going to be lambda 1 alpha 1 square U1. There will be a transpose sign here. All right, so there's a transpose sign that I forgot. So it's going to be lambda 1 alpha 1 square times U1 transpose U1 plus lambda 2 alpha 2 square U2 transpose U2, etc. So again, using the property that these are normalized to unit norm, so the result is going to be alpha 1 squared times lambda 1, alpha 2 squared times lambda 2, etc. So you can write it if you want. This is the summation of lambda I times alpha I squared for the first top term. For the bottom term, it's similar computation. This is x transpose times x. We're computing the norm. And use this decomposition. It's going to be a summation, again, alpha 1 U1, alpha 2 U2, etc. times alpha 1 U1, alpha 2 U2. This transpose here. Exactly the same logic. It's going to be alpha 1 square plus alpha 2 square plus alpha 3 square, etc. It's the summation of alpha I square. Any questions up to this point?
What is the subscript on the magnitude of x squared?
This one here?
Yeah.
It means just a 2 norm. So it's defined. This indicates that this is a 2 norm. Defined. This is a Euclidean norm defined by this. Any other questions? All right, very good. Now let's take a look at this one, right? What would be the worst case when you have this divided by that? Okay, so if you have a bunch of eigenvalues, lambda 1, lambda 2, all the way to lambda max, what is the maximum number for this divided by that? So if you choose around, right? So the key concept is if you let x change and you figure out what is the maximum value here, you can change these indices alpha i's. Correspondingly, you change the contribution of the eigenvalues in this summation. And what would be the worst case? As example, this is actually a technique in optimization. some of you might take. This one, let's do a two eigenvalue case. Let's say I have lambda 1 and then lambda max. Lambda 1 is less than lambda max. All right, so this is lambda 1 times alpha 1 squared plus lambda max times alpha 2 squared divided by alpha 1 squared plus alpha 2 squared. If you only pick, this is a combination of lambda 1 and lambda max. If you pick alpha 1 to be 0, then you get lambda max out of this. If you pick alpha 2 to be 0, then you are selecting entirely lambda 1. Right? And if you pick in between, it's going to be some number in between lambda 1 and lambda max. So what would be the maximum in this computation? So it achieves the maximum when alpha 2 squared is 1 and alpha 1 squared is 0. And in this case, the maximum gives you lambda max. And then it achieves the minimum, which is the smaller one here, when alpha 2 squared is 0 and alpha 1 squared is 1. So this weighted sum is going to be determined by how the weights look like. Any questions? Okay. So this is the main result. The proof is going to illustrate you my main point, that this connects with the energy functions. All right. So let's take a look how we can come up with positive energy functions out of these matrices with properties in the eigenvalues. So we talked about this. Because the eigenvalues are real, we can order them. We can pick the smallest, we can pick the maximum. And if all these eigenvalues are positive, or in other words, the smallest of these eigenvalues is positive, then all the eigenvalues are positive, and the matrix P is called positive definite. So what that means is immediately relevant. A matrix being positive definite, that means from here. So that's going to give us X transpose AX, right? If all these eigenvalues are positive, and you can see this is positive and this is positive, then that's going to guarantee us this is going to be positive unless X is 0. So this will be like a good structure of the energy function that we're going to discuss. So because of this concept, equivalently, this is another definition of positive definite matrices. P is called positive definite, written like that. It's not a positive sign. It is written a little bit curved like that. If X transpose times P times X is positive, for any X that's not 0. If it's not strictly positive, let's say it's positive or 0, then this is called positive semi-definite matrix P. So we have positive definite matrices. We can also have negative definite matrices. Negative definite matrices, just to change these two signs. If you have a matrix, and no matter how you construct your quadratic function, x transpose times px, if you always have the result to be negative, then it's called negative definite. So again, if it's less than or equal to, it's called negative semi-definite. So this sounds a little bit interesting at the beginning, right? Somehow a quadratic function can be always negative and can also be always positive, right? Give me some examples. What would be some quadratic numbers that are always positive? Quadratic functions. This is one, right? Let's do this. It's always positive unless the x's are 0. And then for this one, negative semi-definite, I can do this. Then it's going to be always negative or 0 when x1 equals to x2 equals to 0. So positive definite goes to energy function, and negative definite, guess how it goes to? The derivative of the energy function. We want to show that the energy is going to keep decreasing, so the derivative is less than 0. So that's how it's going to connect. All right, be careful. Positive definite functions, positive definite matrices does not mean that all the entries are positive. So take a look at this example. 2, 2, negative 1, negative 1. It is positive definite, although the entries contain negative values. It's because, let's do a verification. If you have a vector transpose times this matrix times a vector transpose, then recall how these are computed. The diagonal elements going to contribute to the square terms. The off-diagonal elements going to contribute to the cross product terms. So you have 2 negative 1s, and then they're going to contribute to negative 2 in the cross product. So it's 2x squared plus 2y squared minus 2xy. And we can decompose. We can complete the squares using the technique complete squares, right? This is x squared plus y squared plus x minus y squared. So it's always positive or 0. And it's 0 only if these individuals are all 0. So similarly, a matrix with all entries positive does not mean that the matrix is positive definite. So this matrix, it has all the entries to be positive, but it's not positive definite. So you can verify easily by checking 1, negative 1, right? So it's going to pick up the diagonal. It's going to be 1 plus 1 minus 2 minus 2. So you can check that this is negative 2. It's is less than 0. Okay, so usually we check, so this is just one checking point, right? So usually we don't do that. If you want to check like whether a matrix is positive definite or not, we don't try all combinations of vector x here. So instead, we use a tool to check these entries. We use the tool that relates to determinant of a matrix. So this is a necessary and sufficient condition to check. So if you want to check whether this is positive definite or not, we do this. Let's say a 3 by 3 case. We check 3 numbers. The first number is the 1, 1 entry. And then the second number is the determinant of this submatrix, the 2, 2, the first 2 rows, first 2 column matrix. And then the last number we need to check for this 3 by 3 matrix is the determinant. So it's like going this. Check this, the determinant of this entry, first the submatrix, then check the determinant of this matrix, and then finally check the determinant of the whole matrix. So If you check all of them and they are positive, these are called leading principal minors. So if all these are positive, then this is positive definite. If they are positive all 0, some of them are 0, then it's positive semi-definite. All right? That is a tool for checking positive definite or not. Then going one step further, a positive number in a scalar case, what does that mean? Like scalar case, positive number, let's say it's 4. 4 can be decomposed as 2 times 2, right? It's like 2 square. And then positive matrices are matrices such as, similar to this concept, are those matrices that can be decomposed as some sort of a square. It's like a matrix n times n transpose, if it's positive definite. So you can get an understanding of this out of eigenvalue decomposition. We talked about we can do eigenvalue decomposition if P is symmetric. We can do that. So these are diagonal entries in lambda. So this is U. Lambda here can be decomposed as square root of lambda 1, square root of lambda 2, etc. because it's positive definite. So all the eigenvalues, they are positive. So this lambda can be decomposed into this. And then you can see that this is sort of like this matrix times its transpose. You get a n is like a square root of a matrix over here. Okay? So let's do some practice. Let's take a look at these and tell me whether it's positive, definite, or not. Okay, spend a few minutes. You can discuss with your classmate, then tell me the result. So the result should be relatively quick, right? We can use the leading principal minors. For this one, take a look at the first one. It's already negative, so it's not positive definite. And it's not positive definite here either. Now for this one, the leading principal minors are 2, and then the determinant, negative 2 minus 1. So this is less than 0, so it's not positive definite either. Last one, we actually talked about it as an example. So the first leading principal minor is positive, but the second one is 1 minus 4 is negative 3, so it's not positive definite. So that's easy to check. All right, so we have a few minutes left, and I won't start the... So what we're going to talk about next is the utilizing all these in the Lyapunov analysis. So instead of starting the first part of that, I would like to give you an interesting result that provides that leads us to an important equation from now on. The analysis goes as follows. So let's say we have a system, x dot equals ax. So we talked about the concept of energy-like function. let's say V is X transpose P times X. So it's some type of energy function, a quadratic one that looks like that. And P, we'll think about P later, but this is some kind of structure that seems to be suitable to describe the energy. So what we want from today's lecture, right, is that this one is going to be positive. It's going to be a positive definite function. So we want P to be positive definite. And then to judge whether it's stable or not, so we want to take a look at the derivative, energy dissipation. V dot, which is the derivative of X transpose P times X. So it equals, I have two terms that depends on time, X transpose and X. So it equals the first term taking derivative. So it's X dot transpose. So it's AX transpose PX plus X transpose P times X dot, which is AX. So it equals X dot transpose PX plus X transpose PX dot, and equals that. So this equals X transpose A transpose PX plus X transpose PAX. Just to multiply things out, you're going to get X transpose A transpose P plus PAX. So if A is a n by n matrix and P is a n by n matrix, this is still a n by n matrix. This is also a quadratic function. So what we're going to talk about in the next lecture is that under what condition. So from this formula, what we want to judge the system is going to be stable. So what we want, as you can imagine, is that we want the energy to decrease. We want the energy to dissipate. So in other words, we want this one to be, this matrix to be negative definite. So let's define, I want it to be negative definite, let's define it as follows, just for notation convenience. Define it to be negative Q, where Q is positive definite. This matrix equation is called the Lyapunov equation. All right? So it's going to appear again and again from now on in stability analysis, in also the following topics. So that's for today's lecture.